Okay, welcome back, everybody. Day 3 of school, right? Okay, so today we are going to start our official content for the unit. We're going to be talking a little baby bit of physics here. So I'm curious, has anybody in this classroom taken physics already? Okay, some of you. Okay, I have no idea if this overlaps with your physics class in any way. So we're going to go through the basics here as relates to anatomy and physiology. So if you haven't taken physics, that's totally fine. We'll get it. This part is easy. Okay, so we're going to be applying some laws of physics to our understanding of blood flow and pressure so that we can understand the vasculature now and then our airways and our pulmonary system later. Okay. So we already know a bit about gradients. We talked a little bit about pressure gradients in the heart. Now we're going to be talking about larger pressure gradients across systems of blood vessels. All right, so that's going to be one piece that we're paying attention to now. A new thing that we're going to be talking about is a concept called resistance. So this is a new property for us. It's going to be important for understanding how fast blood can flow through a tube, which is really the little aspect of physics that we're going to be drawing on for this unit. And so we're going to be learning about the relationship between a pressure gradient and the resistance of our systemic circulation to understand how our blood moves through our body. Okay. It's easy to demonstrate some of these concepts with air, a bit more than blood. I'm not going to bleed all over the front of the room up here. So we're going to go ahead and think a little bit about how this relates to our pulmonary system first, so we can get a kind of body feel of how these things work. So I want you to start by putting your hand over your mouth and trying to blow the air out. And I want you to feel that pressure building, right? So, right. And then when you release your hand, right, you can feel that pressure release. Right, so that's our pressure gradient if we're thinking about lungs, right? So you build high pressure inside, moving towards a lower pressure outside in the room. So our blood is going to flow the same way in that same direction. Okay, so that's a pressure gradient. And our next piece we're going to add on is resistance, and we can kind of do that physically with breathing too. So I want you to feel the difference between trying to blow air out with your mouth wide open versus with your lips pursed, right? So like versus. And you feel how that flow is different based on how wide your mouth is, how big that aperture is. That's our resistance. Okay. So we have this equation at the bottom of the slide here, going to be really important for us. So do memorize this one. Fortunately, only 3 things in here, very simple. And this is really just a relationship between these 3 ideas, these 3 things that we're tracking, right? How are things flowing? That's the flow part. What's going on with our pressure gradient? So that delta P, the triangle in the P, that's our pressure difference, right? So we're going to take one pressure minus another pressure. That's that delta P. And then we're going to divide it by our resistance. So that's what we were feeling as we were changing how big our mouth is, right? So all we need to know to figure out the flow is those 2 things, the pressure difference and the rate and the resistance. Okay. So how does this relate to our circulatory system? Okay. So our circulatory system, really just the heart is a pump creating pressures. And then we have a closed loop. And the blood is just flowing through tubes in that closed loop. That's what your arteries, your veins, and all our smaller blood vessels are, right? Just a system of tubes taking us from the heart and then back to the heart. Okay. So our pressure through this system is that force exerted by the blood. Okay. Our flow is moving from our high pressure to our low pressure. Right, so from our heart when we squeeze to elsewhere in the body. And then we have resistance out in the body that can change how much blood flow is going to get to different organ systems, or ultimately we'll look at how it can change blood pressure, but that's going to be a future topic for us. Okay, so when we think about resistance, we'll talk about this in detail in the physiology of it when we get to our section on arterioles. But basically what we're going to be doing to change resistance is just changing the diameter of our blood vessels. So we're going to see that our blood vessels can be open wide, or we can squeeze them down, right? And we can make them smaller. And that is going to change that big R on the bottom of our equation, this resistance here. Okay. All right. So if we were looking at just these basic properties in two kind of jars of water connected to each other, we'd find these same physical properties apply, right? So a flow is going to be due to pressure gradients. So we have these two, we might refer to them as hydrostatic columns, right? We've just got columns of water here. Right? And we can see then these columns, these different amounts of water, you can think of them as, like if you were diving down to the bottom of the pool, right? You can feel the pressure is greater when you're deeper, right? So water exerts pressure. Okay. So in this diagram, we can measure pressure differences between these two columns, right? So we can see here a pressure difference between the top of this column and the bottom of this column, right? Our delta P here is 40 millimeters of mercury. That's our units on our pressures here. So 100 minus 60, if we measure in these columns, is 40. And we can see that because there's a pressure difference, this creates some amount of flow from this higher column towards the lower column. Right? So that's our high pressure to our low pressure. Right? That's what our heart is doing in our circulatory system, creating that high pressure, sending us towards areas of low pressure. Right? And we know that as we related that to the heart at the end of A&P 1, right, we know that the heart fills when we have chambers that are really low pressure, and chambers earlier in the circuit that are at a higher pressure, leading blood to flow forward. Okay. So we always need a pressure gradient to exist in order for blood to flow, right? This is why if your heart stops beating, that's bad, right? If your blood stills, right? If we don't create these pressure gradients, blood is not going to flow. Yeah. So that's what we see in B, right? If there's no pressure difference, everything's still, we have no flow. Okay. So a thing to notice in diagram C on this chart is something you might get tripped up about, but hopefully not, is that sometimes you might notice, right, like we have these columns that are filled higher, right? We have numbers for each of these columns, measurements of pressure that are higher, right? So you might think that that could change the flow. So long as we have the same pressure difference, it does not matter what those absolute values are in the two columns, right? So the only thing we're looking at is that delta P, right? So the only thing we look at is the difference between our two pressures, not either of the values on their own, right? So we can see that the flow in this final diagram is the same as the flow in this first one, right? So flow is 20 milliliters per minute in both of them because we have that same pressure difference. Okay. So questions about this part yet? Sweet. Okay. Oop. All right. So a reminder of our directions for our blood flow and our blood vessels, right? We've got our heart. We have our 4 chambers, right? We have our atria on top. We have our ventricles on the bottom, matching that V at the bottom of the heart, right? And we've got right and left. Okay. Now that we're thinking about vasculature, we're going to be paying a little more attention to how do we loop back, right? So we know that we have a pulmonary circuit, right? So we have our pulmonary arteries going out to our lungs, and coming back as pulmonary veins, right? So pulmonary artery and pulmonary vein. That's our pulmonary circuit. And we have our systemic circuit, right? So we have one of our most important big blood vessels, our aorta, right, coming out of our left ventricle. And then as we walk through this unit, we're going to see that we have splits to different arteries. And then we're going to have smaller blood vessels that we'll pay attention to in our different slide decks, in our different kind of pieces of this unit, right? So next we're going to have our arterioles after that. This is where the resistance is really going to be important. Then we're going to have our capillaries in the middle before we flow back. So our capillaries are when we're going to have exchange happening. Capillaries, the main concept we'll think about is what comes out of the blood and goes into the tissue, what goes from the tissue into the blood to get ultimately released. So capillaries. And then we're going to return through venules first. So I just think of those as little veins, and then our big veins here. Okay. And coming into the right atrium, we do have names for those veins as well. We have both a superior and an inferior vena cava. And that's our biggest vein. So analogous to the aorta on the opposite end of this circuit. Good. So we'll walk through each of these pieces throughout the unit, but when we're looking at pressures, right, if we're thinking about our pressure gradient, right, we've got to find some pressure differences. We're going to need a pressure difference at this end of our pulmonary circuit versus this end, right? That's going to have a delta P. And we're going to need one across our systemic circuit too, right? So we're going to measure here versus here. So there we have another delta P, difference in pressure. Okay, so pressure gradients exist across both those circuits, the systemic circuit and the pulmonary circuit. Our generic way of expressing that is this delta P, saying our pressure difference. The main one that we're going to be thinking about is across the systemic circuit, because that's the one that goes out to all the organ systems in your body. The pulmonary circuit is just for the lungs. Okay. And particularly that pulmonary circuit is going to be involved in some gas exchange. Okay. So if we're calculating across our systemic circuit, we have some measurements we could take in the body to figure out how big is that pressure difference, right? So that first equation that we looked at that we're definitely going to memorize, right, was flow is equal to our pressure difference, that delta P, over our resistance. Yeah. And as we walk through this unit, we want to relate this to things you might measure in a clinic, or you might measure if you were doing research, or you might try to figure out ways to make estimates of. We're going to sub in measurable values for those different properties. But this relationship is always at the base of them, always holds true, right? So for our systemic circuit, if we're trying to figure out what the flow is, we can start subbing in values already, right? So for this pressure difference, right, looking at that map of the heart and vasculature, right, we put a dot at the beginning of the circuit, right? So where we have the aorta. So we actually talked very briefly at the end of last unit about our mean arterial pressure, which is an estimate of the pressure in the aorta over the full heart cycle. So that's our bigger value, right? That's the beginning of our pressure gradient. So we're going to sub in that. Yep. So that's our map. And that low pressure coming back to the heart in our vena cava, we refer to as our central venous pressure, so CVP. And we're not going to worry about the resistance part yet, so we'll just leave that on the bottom there. Okay. So you can remember it as always just that flow equals delta P over R, and in your head, kind of logically think about, okay, what value do we need for that pressure difference? What value will we ultimately need for resistance? Or you can learn the rest of these equations in the slides. But honestly, if you logically link them together in your mind, there's a lot less to remember. And really that first equation kind of does a lot of work for you in the end. One thing we will ultimately see before we go ahead, like committing this part to memory, is that when we're thinking about flow through the systemic circuit, that pressure coming back to your heart in the veins is going to be really low and kind of like negligible unless there's some kind of pathology, right? Unless there's something wrong. So ultimately, as we continue to kind of adjust this equation in the future, we can really kind of just assume that that mean arterial pressure is the whole pressure difference. But we'll talk about that a bit later. Now, we do officially have values for each of those. Okay. If we wanted to graph the pressures that we see in our different types of blood vessels, it might look something like this. Okay. So for our systemic circuit here, right, we can see that we have a high pressure in our arteries up here, right? So somewhere looks 80-ish here on this graph, right? And we've got a low pressure when we get back to the heart in the veins, right? And that low pressure, as you can see, is almost at zero, basically zero, for both our systemic circuit and our pulmonary circuit. But if we look at the difference between the systemic and pulmonary circuits, right, we can see that our pressure gradient here, right, our pulmonary arteries are at a much lower pressure than our systemic circuit is. Now, this can kind of raise a question, right, which is your blood has to flow through these things in order, right? So it has to go from your right atrium to your right ventricle, then through the pulmonary circuit to the lungs, to the left atrium, to the left ventricle, and then through the systemic circuit, right? So that pulmonary circuit and the systemic circuit, they're in series, right? So flow has to be the same in each of those circuits, right? You can't like skip over and have like lower flow going to the lungs, but then suddenly there's blood coming out of nowhere flowing through your systemic circuit, right? This is a closed loop. Okay. The reason this can happen, right, the way we equalize that flow is because the pressure difference isn't the only thing that matters for the flow, right? So the other thing that matters to determine how much flow there is through these vessels is that resistance piece, right? So our flow, right? I just keep rewriting this because I don't know why. I really always like division to have a top and a bottom. It helps me out. So I'm not writing anything new than in your bullet point, right? But notice, right? We could have the same flow, even if we have a difference in pressure that's different, if we also have a resistance that's different, right? So if we have a higher difference in pressure and a higher resistance, right, divide by a higher number, we might end up with the same number as something that has a lower pressure difference, but also has a lower resistance. And that is the case when we think about the pulmonary circuit versus our systemic circuit. So that means we got to think in a little bit more detail about this concept of resistance. So why could resistance be different in the different circuits? Now, there are multiple factors that can affect our resistance. Ultimately, there's really only one of them that we're going to care about as relates to anatomy and physiology, because only one of these things is really going to be kind of changeable in your body on a day-to-day basis. So we're thinking of that one first, right? Okay. So our overall equation, if we wanted to reshape it, right, is our, again, I'm just going to rewrite this so that I can see a top and bottom. Our big R is the resistance. Resistance. Okay. We're not going to need to directly calculate this in this course, but if you wanted to, formally, this would be 8 times our viscosity of the fluid. Okay. So viscosity of the fluid, think about that as like, is this fluid more kind of like water, or is it more kind of like honey, right? So like how thick or kind of sticky this fluid is. So blood viscosity shouldn't change too much. It's dependent on your number of red blood cells and the amount of protein in your blood, which should stay constant in your body. So again, certain diseases might affect that. But if we're thinking about the normal, healthy, average person, that's not something that we're really going to be changing. Okay. So up on top as well here, right? We also have L, right? So this is our length of a tube, right? Because this is a physics-related equation, right? Now, this would be important if you were doing something like building a plumbing system for a house, right? How long a tube is would matter. But you are not going to change how long your aorta is, right? So the length of your blood vessels is not really going to change either. If you were comparing maybe an infant versus an adult, you could think about length, but since we're just thinking about, you know, ourselves or a patient in their day-to-day lives, that length is also just going to be a constant for us. But this bottom part is going to change. Okay, so on the bottom here, we have some multipliers, right? So we're going to have pi, okay? And then we have little r to the fourth. Okay, so be careful as we're moving through to pay attention to whether we got a big R or a little r, because those are different things. All right, so our big R is resistance. Our little r is our radius. I'll just write that in here. I want the 4 at the end. All right, so you can see that it's to the 4th power, right? So it's already going to be really important, right? Because we're multiplying it by itself a bunch of times. Okay? And here we can see what our radius is in a blood vessel, right? So this is basically just a measurement of how wide that blood vessel is, right? So diameter would be the whole way across the circle, whole way across the tube, radius just half, right? So this is going to be something that we can change, right? So this is something you can change in your body. We're going to see that this links up to our nervous system, right? So last time we watched that patient video about someone with Parkinson's and NOH, right? So we know that the nervous system played a role in that. We saw norepinephrine in that. We're going to see that those are things that affect resistance and therefore blood flow. And the way they're going to affect those things is because we're going to see that things like norepinephrine have an effect on the radius of blood vessels, right? So our blood vessels are going to be able to get narrower and wider. Okay? So notice, because of the shape of this equation, right? If your radius goes up, right, you're dividing by a bigger number, that means your resistance is going to go down and vice versa, right? So if our tube gets wider, that lowers our resistance, right? So your big open mouth blowing up, that's a big radius, but low resistance, versus our pursed lip, right? That was a narrow radius, right? So smaller, but you can feel how it feels harder, right? So less flow when we have a small radius, increasing our resistance. Okay, so we can see that in one of these basic diagrams as well. All right, so for this diagram, we're going to have the same pressure difference for our tubes A and B, right? So we have the same setup starting with that delta P, ooh, can't even draw triangles well, equal to 40. Okay, so we'd set that up the same for both of these. We can see that we have a difference in flow when we look at A versus B, right? So we have larger flow, more flow, 20 milliliters per minute for A, right? And we have less flow through B, right? So we've got only 10 milliliters per minute through B. Okay? Now we have the same pressure difference. Why do we have this difference flow? This is because of the width of that tube, right? So our radius of this tube is different in A versus B, right? So for A, if we're trying to figure out our resistance, we're gonna be a little squidgy about it. I'm just gonna not say equals. I'm just gonna give that little approximation sign, right? So we're not gonna change the top part of that equation. We're not changing our viscosity or our length, but we are gonna see our radius change. Right, so for A, right, we have a big radius, which means we have a small resistance, right? So we'd see that lower resistance results in our increase in flow. Now, we don't have measurements on the radius of these in this picture, so we're not going to calculate it exactly out. And at this point in the unit, we're not going to be calculating exactly out our flow either. When we talk a bit about how we can sub in measurable values, we might do a couple example calculations, but for now, we just want to be able to generally tell, okay, if this value goes up, what else goes up with it? If this value goes down, what else goes down with it? Questions at this point? Cool. All right. So we got our low resistance for A, and we got this higher resistance in B because of that narrower radius, meaning we end up with a slower flow. Okay. So this is ultimately in your body going to be driven primarily by your arterioles. Right? So coming out of the heart, we're starting with our big arteries. You'll see those in lab. We branch and we branch and we branch. Every time we branch, we get a little narrower till we get to arterioles. You don't really see arterioles in lab, okay? But they're super important. This is where that regulation of resistance is going to come in. So the radius of arterioles, some smaller arteries, can be affected through a couple of different factors, but we're going to see in particular how the nervous system can affect this, but we'll go through intrinsic and extrinsic effects on resistance later on. But we do want to know these two general words for our changes in radius when we're thinking about blood vessels. Okay. So we got vasoconstriction and we've got vasodilation, right? So vaso tells you we're thinking about blood vessels, right? So vaso, think vessels. And then constriction, right? Think boa constrictor, right? When we decrease the radius of a vessel, vasoconstriction, okay? And this means we have higher resistance because we got this narrower tube, okay? When we have vasodilation, think about like if you go to the eye doctor and they put those drops in your eye and your pupil is dilated, right? It gets bigger, right? That's what's happening in vasodilation as well, right? So blood vessel has increasing radius, it's dilating. And this means that we have decreased resistance, right? So like when your mouth is open big and wide, easy to put faster flow through. So we'll see these varying as we look through our systemic circuit. And if we compare our systemic circuit to our pulmonary circuit, I didn't label out the fact that in our pulmonary circuit, we also do have blood vessel branching. We won't think about the specifics of that, right? But in our pulmonary circuit, ultimately, we would have less resistance than in the systemic circuit. And this is why we can have that lower pressure difference, creating the same blood flow. This is a case where you might think about like how far the blood has to travel, right? I did say that we're not going to change the length, which we're not changing the length of any of our blood vessels. But if you want to think about why the pulmonary versus the systemic circuits are different, right? Lungs are pretty close to your heart. Okay. So when we think about things that like physiological variables, we might be tracking in order to put some hard numbers on these things. When we think about resistance throughout the systemic circuit, we're going to be looking specifically at a number we call our total peripheral resistance, TPR, total peripheral resistance. So remember, peripheral out towards the periphery, or peripheral vision out towards the sides, right? So this is out in your body generically, okay? And it's total, so this is just all the resistance of all the blood vessels out in your systemic circuit added together. So we're not going to be tracking specifically how much resistance is here in your radial artery versus somewhere in your leg, right? We're not going to be doing that when we're trying to figure out flow through the whole circuit. We're just going to be thinking about how much resistance is there in the system overall. Okay. So our resistance across a network of blood vessels is going to have to take into account the resistance across all of them at once if we're looking that pressure difference as being at the beginning of the whole circuit versus the end of the whole circuit. Okay. And our flow through that network is going to vary with the resistance if we keep that difference in pressure constant. Okay. So this is going to be true for our systemic circuit. Eventually, we'll talk about, okay, like why might you have more flow to your muscles than to your digestive system at a certain moment in time? Or why might you flip that? Why might you send more of your blood to your digestive system and kind of not send it out to muscles in your arms and legs, right? So a way that we'll be able to redistribute blood flow will be if we look at the network of blood vessels and calculate flow to a specific organ system, okay? But for now, we're going to be focusing just on the whole systemic circuit. Okay? So when we see vasoconstriction in our systemic circuit, in this big network, constriction, narrow radius, smaller radius, meaning we have our increase in resistance, harder to send flow through that system, decreasing the flow. When we blow up our blood vessels big and wide, vasodilate, now we have less resistance, increasing the flow through our circuit. Okay. We're not going to warm up, but let's use this as a practice question anyway. Okay, so let's pause for a second and think about this little tube that I've drawn for us. Okay, so right here, we're looking at flow from A to B, right? So at A, we have a measurement of 100, and at B, we have a measurement of 50, okay? So using these two relationships, these two equations that we just learned, I want you to think about if we increase that pressure at A by 50, what would happen to our flow here? All right. That's part one. Part two, we want to think about what would happen if we increased both A and B by 50. And then part three, we're going to think about what if we shrunk the radius of this tube, right? So what if we narrow it down so that it's like half the size? Okay, so take a second to answer for yourselves in your notes each of these three questions. Let's walk through it. Is that what I put in these questions? Okay, yeah. So starting out, okay. So for that first question, let's go ahead and answer all together. What's going to happen if we increase that value at A, that pressure at A, by 50 millimeters of mercury? Let's take a peek. Okay, cool. Yeah, so in this case, we're going to see an increase in the flow, right? So what we've done, right, we know our flow is our difference in pressure divided by our resistance, okay? So when we increase A, right, I think at A we had to start with 100, right? And at B, we had 50, right? So originally we had this flow from high to low, so from A to B, okay? And now we're saying we're jacking A up to 150, but we're leaving B alone, okay? So now we have a larger pressure difference, right? So we've increased this difference in pressure. We're not doing anything to the radius or the resistance yet, right? So this is what creates an increase in flow here. So our flow increases for this one. All right. So part 2, what happens if we increase both A and B, increasing each of them by 50? Okay, let's take a look. Okay. Yeah. So in this case, right, we still have that same relationship we're looking at. Flow is our pressure difference divided by our resistance. We're still not changing the resistance. Originally, we had A at 100, B at 50. All right. Meaning we had our pressure difference as 50. All right, so the change we've made is we've increased each of these by 50. So we've got 150 now. And I've got 100. Okay, so we still have that same pressure difference. Our delta P stays the same. It's still 50. Right, so there's no change to our flow in this example, right? So it doesn't matter how big these values for A and B are. All that matters is the difference between them. Right, so no change in the flow for number 2. Oop. Okay. Let's scroll back to that number 3. Looks like I didn't put a question for that one. Okay. So what about, I probably did. Let's see. Sorry, guys, I got too ahead of myself. So we'll get back to the resistance question in a second. But what do you think we're going to be thinking about when we think about flow, right? So we have measured our delta P, right? We know that ultimately what we're going to be using that is our mean arterial pressure, primarily, minus our CVP, our central venous pressure. We now know a new term that we're going to use for our resistance, our total peripheral resistance. So ultimately, we're going to add up resistance in all our blood vessels for resistance. And we're going to see a familiar quantity when we think about flow. Anybody have any ideas? Mm-hmm. Yeah, perfect. Our cardiac output is going to be our flow, right? Because we're going to be thinking about how much blood goes through per minute, right? So liters per minute, milliliters per minute. Flow is going to be our cardiac output. So when we think about those two first questions, right? Oops. Oh, this is what happens when I do stuff too early. But great, now we know the answer to the radius one. Yeah, so when we think about those first two questions, right, we're going to see if you increase your mean arterial pressure, so the pressure in your aorta, without making any changes to what happens in the veins, you're going to see that we increase our flow through the system, right? And that's going to be related to our cardiac output, right? If both our central venous pressure and our mean arterial pressure go up by the same amount, flow would stay the same. Ultimately, when we relate these to cardiac output, rather than thinking about the blood vessels affecting how much blood your heart pumps out, we are going to be reshaping that equation a little bit so that we can solve for a different value, right? So that we can actually solve for what is that pressure difference? What is your mean arterial pressure? But that's going to come in a little bit. Okay. So for that third question in the example, we're thinking about what happens to our system if we have a change in the radius, right? So this is where we're thinking about the relationship between radius and resistance, right? So we were thinking, right, we have our flow. In this case, we're going to leave our delta P the same, our pressure difference the same, but we're going to see that resistance changing, okay? Our resistance changes in the opposite direction than our radius does, right? So resistance is going to be like the inverse with some exponents of our radius, right? So in this case, we had our radius shrinking, radius went down, which means our resistance goes up, okay? So then we take this, put it into the larger equation, okay? So our resistance went up, and our flow has to go down. Right? So when we think about radius and resistance, we do have kind of a two-step process that we think about in our heads. But after you do it several times, I think it'll become kind of second nature, because sometimes you can feel it, right? You can also think about resistance if you think about trying to drink a milkshake, right? That milkshake straw is really big, it's really wide, it has this really large radius, because it would be super hard to drink a milkshake through a tinier straw. Okay. So here's where our cardiac output comes into play, okay? So if we want to put in actual physiological values in for our flow equation, right? We've got our mean arterial pressure minus our CVP, but that's basically 0, so we're going to ignore it for our purposes. We're here, okay? So mean arterial pressure, so average pressure in the aorta, basically, divided by total peripheral resistance. So that's all the resistance out in all the blood vessels in your body. And we'll think later about how that can change, but mainly it's things that affect the radius. And our flow is our cardiac output here, right? So when we see equations later on, right, there's still going to be versions of this flow equation, right? But if we're trying to figure out, okay, how are we affecting mean arterial pressure, right? We might have that as our unknown, but we might know the resistance and the cardiac output, right? So we could move things around. So we leave mean arterial pressure alone on one side and multiply together cardiac output and resistance. Okay. So this is still that same relationship. This really is the same equation. We've just moved stuff around so that we isolate the thing we're trying to solve for. Right? So when you see more equations in the rest of the unit, they're mostly going to be just different versions of this same thing. All right. So we will stop there. Next time, we're going to get into thinking about the arteries and the arterioles.